try and get as much of the notes on 2.2 and 2.4 as you can for part of tomorrow's homework. All right, we're going to look at patterns today because a lot of math was developed because you had curious people, these old mathematicians that you'll eventually research. They were looking at patterns and then describing them in terms of mathematics. So I want to see if you can pick out patterns. Some patterns are number patterns, some are picture patterns. This one's kind of a word pattern. Describe the pattern and find the next item in the pattern. Patterns January, March, May. Who can read it? And what was that?
It said July.
You did say July. Now describe it.
It says January, March, skips April, May, maybe it's June. I don't know.
So how did you make a guess of what to complete it with?
I don't know. I just threw it out there.
All right, let's try Morgan.
They went from January, they skipped February, March, skipped April, May, skipped June, and July.
Okay, so they're giving us every other month. They're skipping one and then giving us the next one. They described it as alternating months of the year. July was the next one. All right, here's a number pattern. Describe the pattern, find the next item. Let's try not to shut it down. Change the thing. What's the next thing in the pattern and describe it. Our chicken. 35, well describe it so I can see. Add 7, add 7, add 7, add 7, okay? They described it as multiples of 7. They didn't say add 7. What's multiples of 7?
It's like 7 times 1 is that number, 7 times 2 is the next number, 7 times 3 is that number.
4, 7 times 5. Okay. So that would be another way to describe it, but it's the same pattern. All right, picture pattern. How do we have to draw this one on your paper? What would it look like? Maybe you know what shape it is, but it's important which way it is turned and basically how it's drawn. What's the next shape in that pattern going to look like? It's obviously going to be a triangle. Which way is it going to be turned? The way it should turn, it looks that way. Vertical and then point off to the right. Now to describe it, notice what their wording was. In the pattern, the figure rotates 90 degrees counterclockwise each time. Counterclockwise, like backwards from the clock. So think about taking that first one and turning it a quarter of a turn, turning it another quarter, and then a third one. There's a number pattern again. What's next in the pattern? And how would you describe it? Decimal point, 3 zeros and a 4. He's close, but I wouldn't count that right. Why would I not count it right? Here's what he said. I wish I could write up there, but they haven't figured it out yet. 0.0004 is not the next thing in the pattern. You need a 0 in front of it because that's what was in all of those. So put a 0 in front. And then that's what comes in next in the pattern. Now, how would you describe it? Is that a way to describe it, Lucas? No. How did you know to do what you told me?
So just adding a 0 behind the point every time.
Okay, he's adding a 0 behind the decimal point, but in front of a 4 every time. Connor?
It's divided by 10 every time.
Which would be like dividing it by 10.
Or tens, hundreds, thousands, 10,000.
Okay, so they're putting the 4 in the next smaller decimal or column, I guess. All right, I think I went with dividing. Nope, I guess I went with the one where 0. That idea. Here's a number pattern. Once you grab a marker board there, the whiteboard, tell me what comes next. If you can put down a describing, so that I can tell what you're thinking. What's next? Things that I think of is, okay, is it going up? Is it going down? Obviously it's going up. How much does it go up each time? And if it goes up by a different amount each time, is it that we're multiplying to get the next one? What are we doing? Before I call on someone, I'm gonna look at the boards, see who's got an idea and who doesn't. Okay, show me your board so I can see who's figured it out. All right, those that are showing me are all agreeing. Can't really see everything. Okay, I don't see what comes next in the pattern. All right, it should be 36. Okay, now what were ways to describe it? Adding the next odd number. So you added 3 the first time, then added 5, then 7, then 9. So add 11 to get the next one.
X to the second power.
So 1 is 1 to the second power, or 1 squared. And then 2 squared would be 4. 3 squared would be 9. 4 squared. So these are, they're called the perfect square numbers. Next digit squared. Right. And both of you got 36 for your next one? Right. 2 different ways to describe the pattern. I went with the perfect squares, but you could do the adding odd numbers idea. Hey, here's an interesting one. This is called the Fibonacci sequence. It's actually a pretty famous sequence. It starts out with 1 and 1, and then the pattern begins. This is a pattern that shows up a lot in nature, like the number of leaves or petals on a flower. You know, the inner ring has 1, then the next ring has 2, then the next one has 3, then the next one has 5. So it tells you how many would be on each ring of like petals, or they often show seashells, the parts in that shell. How would you describe
so it's 1 plus 1 equals 2, and then 1 plus 2 equals 3, then 2 plus 3 equals 5, then 3 plus 5 equals 8, then 5 plus 8 equals 13, and 8 plus 13 equals 21.
21's the next thing in the pattern. What was he adding? He was adding the two previous numbers to get the next one in the sequence. Add the two previous numbers to get the number. How many got that figured out before he told you? Or half of you did? Okay. That is the Fibonacci sequence. Okay, let's do a picture pattern. Got your boards you can draw. Describe it and find the next item in the pattern. Can you tell there's a color difference up there? So you've got your board, you can do the correct colors. Haven't been able to do that before. That picture pattern was a little bit harder to do. Here's what it looks like when you're done. All of those connecting parts in there. All right, question on that one. Do you think for you are generally the number patterns easier or picture patterns? How many think that for you number patterns are easier? Picture patterns? A couple people on that? All right, what we're doing when we look at patterns is called inductive reasoning. So back to your notes there. Take that over. Back to your notes. When several patterns, or when several examples form a pattern, and we assume that that pattern continues, we're applying what's called inductive reasoning. So your definition, inductive reasoning is the process of reasoning that a rule or statement is true because specific cases are true. Specific cases, that could be like what we were just doing, looking at examples. The first case, the second case, the third case in the pattern. So inductive reasoning is based on patterns. The conclusion that you come up with from the pattern is called a conjecture. Now the conjecture that you were giving me when you were saying basically the next number in the sequence is 36, that's your conjecture. That's what you believe to be true. In science, what do you call what you believe to be true? Hypothesis. We will be using the term hypothesis, but it has a different meaning in math logic than it does in science. So one of those terms that is different. So what we believe to be true is called your conjecture. So we're going to try and do a few conjectures. It says find a pattern and complete the conjecture. Now what it means by find a pattern is the problem stating that we want the sum of two positive numbers. So make an example that is the sum of two positive numbers. 5 plus 7, that equals 12. That's one example. How many examples do you have to have before you can come up with a pattern? One, like if I told you it's a number sequence and 10 was the first number, could you tell me what the next one is? No, you need a few so that you can get it set up. So how many? Would 2 be enough? 3?
Yeah.
Probably starting there. Some you might need more, but as a minimum 3. So I just thought of one example so far. So we need to come up with 2 more where it's the sum of 2 positive numbers. And don't stick with the same numbers like 1, 2, 1 plus 2, 2 plus 3, 3 plus 4. When you're using consecutive numbers, maybe there's a pattern there that's different than if you used 500 plus 652. Maybe, can you use negatives? No, this one says positive, so can't do that. Can you do decimals, fractions? So don't limit yourself to just one type of number as you're trying to do the examples. So I came up with a whole bunch. Got some integers, some decimals, I even threw in some fractions. Now what I'm going to try and do is fill in the blank to describe the pattern, to complete the conjecture. I think that the sum of 2 positive numbers is, what do I say? I can't say even or odd. I can't say an integer or a whole number because of that fraction. What am I going to put in the blank? Be positive? Positive? The sum of 2 positive numbers is positive? Are all of those answers positive up there? So each of those examples? Yes, so it seems reasonable that yes, filling in the blank with positive in that problem would be correct. Okay, so the conjecture is we think that the sum of two positive numbers is always positive. Is that absolutely true? I don't know, but it's our best guess at what is true. All right, so work on this one for me. Complete the conjecture. Find a pattern, so you need to come up with some examples. You need to see at least 3 examples on your paper. And then you can try and fill in the blank. More than 3 examples is perfectly fine. But don't make examples all the time, all the period, and then not able to finish the problem. Okay, so you need to make the product of 2 odd numbers. Anyone stumped on product? Product, what does it mean? Sum means add. Product doesn't mean add. What does product mean? Product means multiply. So you need to make some problems where you're multiplying 2 odd numbers. Pick a variety. It doesn't say they have to be positive. I don't think you'd really use decimals or fractions because we don't really talk about odd numbers as being decimals or fractions. But pick some odd numbers, multiply them together, see what kind of answer you get. At least 3 examples before you fill in the blank. How do you describe the type of answers you're getting? Product of 2 odd numbers is this one? Okay. Then what do you come up with? Did you complete the blank? Give me one of your examples. 3 times 3, and the answer is 9. Okay, another example. Vanessa, what'd you use? Which is? Okay. What did you come up with, Zach, for an example?
5 times 3.
15. So I'm trying to think. 9, 77, 15. What kind of answers am I getting? Odd. Okay, so that one was odd. Now I did throw in a negative or some negatives in my examples. Because if I didn't have, like this one, I might say that it's always a positive odd number. So you want to describe it as close as possible, but not incorrect. All right, here's a little bit different kind of conjecture. It says, I want a calculation rule in terms of n, so like a formula that has n in it, for the sum of the first n odd positive integers. So I'm adding up odd integers. I'm adding 1 odd integer, I'm adding 2 odd integers, 3 odd integers, and I want to see how I can get what the total of them would be. A little bit harder one. Let's kind of make a pattern, a table. Start building this table on your notes. The first part of the table is going to tell me how many odd numbers. So 1 odd number, 2 odd numbers, and not just any odd numbers, but the first positive odd numbers. So the top just tells me how many there are. On the bottom of my table, I'm going to put what the sum of those integers is. And sum means adding together. So on the first one, I'm just going to have 1 odd number. And it has to be the first odd number, the first odd positive number. So what's the first odd? 1, okay? So what's the sum of the first odd number? Just 1. What's the sum of the first 2 odd numbers? talking about 1 and 3, what's their sum? 4. The first 3 odd numbers, 1, 3, and 5, add up to be 9. 1 plus 3 plus 5 plus 7, 16.
It's like the perfect squares.
Okay, you notice that's the same pattern we had a little while ago, the perfect squares? Okay, so what kind of a formula could you give me that if I say, you know, the second number, you could automatically come up with 4 without having to expand it out? So that if I said, what's the 20th one, you would be able to come up with it. So what kind of formula would we use to get that total? And he's catching on because that's how he described that pattern earlier. Not x, but n squared in this case. Okay. So the total, if I had 20 odd numbers, they would add up to 20 times 20 or 400. If I had 100, the first 100 odd numbers, they're going to add up to whatever 100 times 100 is. 4 zeros, so 10,000. So that would be how you would complete that conjecture. A little bit different than what we were looking at for the like sum or difference of something. Did that one make sense? Now notice the formula way you couldn't say add the next odd number. Okay, here's one that's completely something different. Make a conjecture about the lengths of male and female whales based on the data. So is there a pattern in that data somehow that you can describe? It's probably not exactly the same kind of pattern we've been doing, but can you make a conjecture, a prediction that you think is true about the length of male and female whales based upon that information? Kind of like, what do you see in that information? Open-ended, there could be various things for you to tell me.
Female whales are generally longer than male whales.
Female whales are, what did he say, generally? Can you say female whales are longer than male whales?
Not all the time.
No, because that last female was 47 inches or some feet, I guess, and there were some males that were longer. So throwing the word generally maybe helps make his conjecture more true. Anything else? Another way to state something? We're going to just go with Connor's idea? Don't want to think yourself anything? Right, the other idea I had was if you averaged all the female whale lengths, you're going to get a number that's greater than the average of the male whales. So we can't give an absolute rule for all of that data, but there's kind of a pattern there. So perhaps a little bit more just out in the world kind of conjecture. All right, now to show that the conjecture is true, you have to prove it. And we're going to be working on proving in a few chapters. To show that it's false is easier. So we're going to start there. We're going to start trying to prove something false. To show something's false, you simply have to find one case or example that demonstrates it's not true. And that's what a counterexample is. You got some notes on what a counterexample is? Fill in the blanks. A counterexample could be a drawing, a statement, like 4 plus 5 equals 9, which is not an even number, it's an odd number. Or a number, maybe if you just say use x being 15, and it will be false. So you're not trying to rewrite the statement. I know there are some teachers that if the statement is false, they want you to change it so that it's a true statement. That's not what we're doing here. We're just coming up with an example. So for instance, if I go back to the whales, which I think was here, if Connor had said that female whales are longer than male whales, we would have had a counterexample. We would have had a counterexample by saying this last female whale was only 47 feet long, and that's shorter than some of the male ones. So that would be the counterexample to what the conjecture was. Is a conjecture true? Not necessarily. It's what you believe to be true, but it's not always completely true. So we're going to think about counterexamples here for a little bit. All right, show that the conjecture is false by finding a counterexample. So this is what someone thinks, that for every integer, if I call it n cubed is going to be positive. What are integers?
A number.
What kind of number? Integers. Come on, algebra background. What are integers? Are they positive?
No, not always. Yeah, always.
Are they negative?
Sometimes.
They could be positive, could be negative, not decimals, not fractions. So when you're making your numbers on your number line, those are your integers. So think of an integer, cube it, and the conjecture says you're going to get a positive. Anyone have a counterexample? You picked one, cubed it, and it wasn't positive? Got 2 hands up. 3, 4, 5. Getting a few more. A number, an integer, that when you cube it, it's incorrect that it's positive. Okay, what number were you thinking of?
Negative 3.
-3. Positive 3, when you cube it's still going to be positive. Okay, B? -13.
Negative
Okay. Okay. So negative something. When you take -3, for instance, and cube it, -3 times -3 is 9, times another -3 is -27. You take a negative and cube it, you're always going to get a negative something. So we came up with like 3, 4 different counterexamples. So the counterexample here, I'm not rewriting it. I actually came up with -3 also. -3 was my counterexample because it shows the conclusion that's in that statement is demonstrated that it's incorrect. All right, everybody get up and touch 2 walls and sit back down and we'll do the next example. You didn't move very far.
Yes, I did.
Don't need to get on that.
No, I'm writing down the assignment that I need to redo.
Oh, from your grades?
Yeah.
And you need to retake that test.
Yeah, I know.
All right, making you think a lot today. Interesting socks there, Connor. I just noticed those. Interesting. I would conjecture that Connor likes back. Okay, now hopefully there's oxygen to your brain. Show that the conjecture is false by finding a counterexample. Okay, so the statement that we think is true, or whoever wrote this thinks is true, they think that 2 complementary angles are not congruent. Can you prove them incorrect? You need to come up with 2 complementary angles. Think of 2 complementary angles, and then think, okay, are they not congruent? Or am I showing that it's incorrect? So in other words, that they are congruent. Come up with a counterexample, 2 complementary angles that are congruent. What your definitions are, here's your last chapter, just needs to stick with you. 2 complementary angles. It says they are not congruent. Can you prove me incorrect? Did you think of this one yet? Not yet? Okay, think of 2 complementary angles. I'm trying to show that it's incorrect what's up there. Katie, what'd you have? 45 and, okay, are those 2 complementary angles, 45 degrees and 45 degrees? Yeah, they add up to 90. And did she show me that it's incorrect, that they are not congruent? And she gave me 2 that are congruent. So that was a counterexample. It's kind of confusing when it says not and you're trying to prove that they are, but read carefully. Okay, here's a chart again. It's not the whales, but show that the conjecture is false by finding a counterexample. I think that the monthly high temperature in Abilene is never below 90 degrees Fahrenheit for 2 months in a row. Prove that my thinking is incorrect. Can you prove that incorrect? Okay, so December, then January, and then February, that's even 3 months in a row that it's below 90 degrees. He probably didn't even need to give me 3. If he would just said January and February, that would be a counterexample, or just December and January, correct. So there are counterexamples in that one, so I'm showing that the conjecture, the statement up there was false, because I could demonstrate it by a counterexample. Okay, back to kind of a math one. For any real number, okay, what kind of numbers are real numbers? It might keep going, but pretty much any number, okay? Any number that, it could be a repeating decimal, could be pi. Pi's a decimal that never ends, that's a real number. Probably any number that you can think of is a real number. Now there are numbers that you haven't been introduced to yet, probably. They're called imaginary numbers. And it's not that they're imaginary, but they involve the square root of -1. You can't do the square root of a negative, but in our upper mathematics, you have to be able to calculate with it. So we introduce what's called an imaginary number. So for any number that you can think of, test this out. Is your number squared always greater than or equal to the number you started with? And if you say yeah, then that's agreeing with it. You haven't found a counterexample yet. So think of another number. Take your number and square it. And compare it. If this is true for your number, you're not finding a counterexample yet. Can you come up with a number that, when you put it in there, it doesn't end up to be greater than or equal to? Jacob thinks he has one. Connor? Any kind of number. Try positives, try negatives, try fractions, try decimals, try integers. You come up with something that shows that's incorrect. How many do you have now? 1, 2, 3 people? Boy, you're gonna have to think today, aren't you? Not trying to find something that fits that, you're trying to come up with a combination that shows that's wrong. Jacob, what do you think of? A decimal that's less than 1 but greater than 0. So if we thought of a half, like 0.5, maybe that would work? Okay, so think of 0.5. What's 0.5 squared? 0.5 times 0.5. 0.25. Is that greater than or equal to 0.5? It's greater than 0.5? 0.25 is smaller. So Jacob's coming up with something that shows this conclusion is incorrect. So you did describe it well. Decimals between 0 and 1. Connor, what'd you have? 0.4. Okay, so that falls within the range there. Anything else? Could I use 0? 0 squared, 0, is that greater than or equal to 0? It is equal, so it fits what's here, so it's not a counterexample. So I think what Jacob described to us was exactly, I put it in fraction form instead of decimal, but what you were talking about was correct. How about one back to our class? Supplementary angles are adjacent. That's what I think. Supplementary angles are adjacent. In to demonstrate that I'm wrong. Probably have to draw a picture, because adjacent has to do with what they look like. So draw me a picture of two supplementary angles, which means you're gonna have to put degree measurement in your picture, right? So many degrees, so many degrees. I think they are adjacent. Can you draw me two supplementary angles that are not adjacent? You gotta think, what does adjacent mean? Draw me a counterexample. Demonstrate my thinking is not right. Could I draw a 120 degree angle and a 60 degree angle? Would those be supplements? Could I draw them so they're not adjacent? Do they always have to be adjacent? Picture? You want to be wrong? Anyone figure out how to do this? It's really not that difficult. You're all just thinking in the same way.
Yeah, you just have, two in one middle.
Okay, do you have, okay, looking at these, are they supplements? You've got three angles there.
Well, yeah, these ones.
1 and 3. Okay, are those two by themselves adding up to 180? The angle 2 to go with it. So that didn't work. Morgan, did you have an idea? I'm getting students to think. Not everybody's thinking and coming up with it yet. Okay, that would be where they are adjacent. This is where they're not. So if I go back to what she, not what she circled, but what she was thinking to start with. Okay, here's a picture. I don't remember her degrees. 63 degrees?
And 117.
But don't hook it on. She's gonna go over here. This angle's 117 degrees. Are those supplements?
Yeah.
Yeah? Are they adjacent? No, there's a counterexample to the statement. So most of you were drawing it together. You needed to get them pulled apart so that you could have them not being adjacent. I didn't pull mine too far apart, but kind of the idea there, pulled apart. So good. Got to think kind of outside the box a little bit. So the steps that we're doing inductive reasoning. We're working with patterns. Look for a pattern. Make a conjecture. What's a conjecture? Statement that you believe to be true based on inductive reasoning. And then step 3 is proving the conjecture, which is kind of hard to do, and we really haven't talked about how you prove it yet. Or find a counterexample. Counterexample is an example that demonstrates the conjecture is false, and so that would demonstrate that it's false rather than it's true. We'll work on proving in a little bit, a couple more days, but we're focusing on proving it false right now, if possible. All right, let's get some time on homework. I haven't been giving you too much time. Let's use the last 10 minutes or so, 10, 15 minutes on that. We've gone through quite a few examples. So let's do the assignment, which is starting on page 77. Today we're going to do 1 through 13, the odds, 18 through 26, the evens, 37 to 39, and 48 to 51. Now tomorrow, since we're trying to do two sections that are related, I want you to try and have some of those notes done ahead of time. So if there are parts that you can listen to and focus on instead of having to write the notes. So I would like you to get notes for sections 2.2 and 2.4 from the e-backpack PowerPoints.
So finish those completely.
I'm not gonna say that everything, there might be some things that I say rather than they're showing up in the PowerPoint, but try. So yes, try and get all of the notes finished for those two. I'll go through examples with you, so you wouldn't have to necessarily worry about all the examples, but if you can get the material as far as the information. Does that make sense, Grant?
Yep.
So you wouldn't have to go through every example, but get the notes filled out. Basically, I want you to have read through and thought through that material before class tomorrow. Doing the notes should help that.